Imagine our sun, a steadfast companion that has shone brightly for billions of years, suddenly swelling into a colossal red giant, engulfing planets in its fiery embrace. This isn't a distant sci-fi scenario, it's a cosmic inevitability. The life cycle of sun-like stars is a dramatic tale of transformation and destruction, culminating in the ethereal beauty of planetary nebulae. In this video, we'll witness the sun's dramatic final act, a spectacle of cosmic proportions that will leave you in awe. Prepare to journey through the fiery demise of stars, where the old gives way to the new, and the universe's grand recycling program is on full display. This isn't just the end, it's a beginning, a rebirth written in the stars. Stellar evolution, a brief overview. Stars, like living organisms, go through a life cycle, a process astronomers call stellar evolution. It begins in a stellar nursery, a vast cloud of gas and dust. Here, gravity plays the role of a sculptor, pulling the material together until it forms a dense core. This core becomes a protostar, the embryonic stage of a star. It's a quiet, unassuming phase, much like a seed buried in the soil, waiting for the right moment to sprout. The protostar grows by accreting more material, growing hotter and denser until nuclear fusion ignites in its core. This is the birth of a star, a celestial being that will shine for millions or even billions of years. The life of a star is a delicate balance between the inward pull of gravity and the outward push of nuclear fusion. For a star like our Sun, this balance is maintained for about 10 billion years. The star spends most of its life in the main sequence phase, a stable period where it shines steadily, converting hydrogen into helium in its core. It's a mature star, confident and radiant, much like a tree in full bloom. But all good things must come to an end. When the star runs out of hydrogen in its core, it begins to die. The star's outer layers expand and cool, turning it into a red giant. It's a dramatic transformation, a star swelling up like a balloon, its outer layers puffing out into space. The core, meanwhile, contracts and heats up, starting to fuse helium into heavier elements. The red giant phase is a tumultuous time for a star. It's like a tree shedding its leaves in autumn, a sign of its impending demise. The star's outer layers are unstable, pulsating and ejecting material into space. This material forms a beautiful, glowing shell around the star, a planetary nebula. The core, now a hot and dense white dwarf, illuminates this shell, creating a stunning cosmic display. It's a stark contrast to the star's previous life, a final hurrah before the star fades away. The white dwarf, meanwhile, slowly cools down, turning into a black dwarf. It's the end of the line for a sun-like star, a quiet, cold remnant of what was once a radiant celestial being. The material ejected into space during the red giant and planetary nebula phases becomes part of the interstellar medium, the raw material for new stars and planets. It's a cycle of life and death, a testament to the universe's ceaseless creativity. The main sequence, where sun-like stars spend most of their lives. In the vast canvas of the cosmos, stars like our Sun spend the majority of their lives in a phase known as the main sequence. This is a period of stability, a golden age where stars shine brightly, fusing hydrogen into helium in their cores. Our Sun, a typical main sequence star, has been in this phase for about 4.6 billion years and will remain so for another 5 billion years or so. During this time, stars maintain a delicate balance between the inward pull of gravity and the outward push of radiation generated by nuclear fusion. They appear as steady, unchanging points of light in the night sky, a testament to their internal equilibrium. Picture a star as a cosmic juggler, keeping numerous balls in the air simultaneously. In the main sequence, the star's core is the stage where the main act happens. Hydrogen atoms are squeezed together to form helium, releasing a tremendous amount of energy. This energy pushes outward, creating a counterbalance to the star's own gravity, which is constantly trying to collapse the star inward. It's a dance of cosmic proportions, a ballet of forces that keeps the star stable and shining. The surface of the star, or photosphere, is where the light we see is emitted. It's a roiling, turbulent place, with temperatures around 500 degrees Celsius for a star like our Sun compared to the core, which can reach temperatures of 15 million degrees Celsius. The surface is relatively cool. Yet, it's here that the star's light and heat are born, radiating out into the cosmos. Contrast this with the later stages of a star's life. As the hydrogen in the core is depleted, the star begins to change. It swells into a red giant, its outer layers expanding and cooling, while the core contracts and heats up. The once stable juggler is now dropping balls, its internal balance disrupted. The photosphere expands, and the star's surface cools, turning a reddish hue. This is a stark contrast to the main sequence, where the star was a picture of stability. The red giant phase is a time of transition, a prelude to the star's final act. Eventually, the star will shed its outer layers, creating a beautiful planetary nebula, while the core remains behind as a white dwarf, slowly cooling over billions of years. It's a dramatic end to a star's life, a final performance after billions of years on the main sequence stage. Nuclear fusion, the powerhouse of stars. In the vast theater of the cosmos, stars like our Sun perform a grand ballet of light and energy, with nuclear fusion as their relentless choreographer. At the heart of these celestial dancers, gravity and pressure conspire to fuse hydrogen atoms into helium, a process that releases an astonishing amount of energy. This is the powerhouse of stars, the engine that has been burning brightly for billions of years. The Sun, a middle-aged star, has been steadily converting hydrogen into helium in its core, a process that will continue for another 5 billion years or so. It's a testament to the incredible efficiency of nuclear fusion, a process that is both the birth and the life force of stars. As stars age, their nuclear fusion processes evolve, painting a dramatic picture of change and transformation. In the core of a Sun-like star, hydrogen fusion into helium is the primary source of energy. However, as the star exhausts its hydrogen fuel, it begins to fuse helium into heavier elements like carbon and oxygen. This marks the beginning of the end for the star, as it starts to bloat and cool, becoming a red giant. The once vibrant star now appears swollen and sluggish, a stark contrast to its former glory. The red giant phase is a tumultuous time, with the star's outer layers expanding and its core contracting, setting the stage for the next act in this stellar drama. The final act of a Sun-like star's life is a spectacular display of light and color as it sheds its outer layers to form a planetary nebula. The core, now a dense and hot white dwarf, illuminates the expelled gas, creating a glowing, ethereal shell. This is the star's last hurrah, a final burst of energy before it fades into obscurity. The planetary nebula phase is relatively short-lived, lasting only a few tens of thousands of years. Yet, it is a crucial part of the star's life cycle, as it enriches the interstellar medium with heavy elements, seeding the next generation of stars and planets. The death of a Sun-like star is not an end, but a beginning, a cycle of life and death that has been playing out in the cosmos for billions of years. The red giant phase, a star's expansion. In the vast theater of the cosmos, stars like our Sun age with a dramatic flare, undergoing a transformation that would make even the most seasoned Hollywood star envious. As a Sun-like star exhausts the hydrogen fuel in its core, it begins to die in a spectacular fashion, first swelling into a red giant. This phase is a stark contrast to the star's previous life. Once a stable, middle-aged star, it now becomes a bloated, cool, and luminous red giant, shedding its outer layers in a slow, steady process. The star's surface cools, turning a deep, fiery red, while its outer envelope expands to hundreds of times its original size. Picture a once modest actor now taking center stage, commanding attention with its sheer size and brilliance. The red giant phase is a time of intense activity. The star's core, now composed primarily of helium, begins to contract under gravity's relentless pull. This contraction heats the core, igniting helium fusion. Meanwhile, the outer layers of the star, now far from the core, cool and expand. This expansion is not uniform. The star's outer layers become unstable, pulsating and ejecting material into space. It's as if the star is shedding layers of old costumes, preparing for its next act. The ejected material forms a circumstellar envelope, a shroud of gas and dust that surrounds the star. This envelope is visible to astronomers as a faint nebula, a ghostly reminder of the star's past. The contrast between the star's former and current states is striking. Once a steady, reliable source of light, the red giant is now a variable star, its brightness fluctuating as it pulsates. The star's surface gravity weakens, making it easier for material to escape. The star's winds become stronger, carrying away more material. This mass loss is significant. The star can lose up to half its mass during this phase. The red giant's expansion also means that any nearby planets will feel the heat. For instance, in our solar system, the Sun's expansion will engulf Mercury and Venus, and possibly Earth. It's a dramatic change, a stark reminder of the universe's relentless evolution. Yet, this phase is not the end, but a prelude to the star's final act, the formation of a planetary nebula. Helium flash, igniting the red giant's core. In the grand theater of the cosmos, stars like our Sun put on a spectacular show as they approach the end of their lives. After billions of years of fusing hydrogen into helium in their cores, these stars enter a phase known as the red giant branch. The core, now a dense ball of inert helium, grows steadily, while the outer layers expand and cool, turning the star into a bloated red giant. This is a dramatic transformation, a stark contrast to the stable, middle-aged star it once was. The red giant's surface cools, glowing a deep, rusty red, while its outer layers puff up, sometimes engulfing nearby planets. It's a slow, inevitable process, a star's last gasp before its final act. Deep within the red giant's core, something extraordinary is about to happen. The helium ash, once a passive byproduct of hydrogen fusion, begins to heat up. The core grows denser and hotter, a ticking time bomb. Then, suddenly, it reaches a critical point. The temperature soars to about 100 million degrees, and the helium atoms begin to fuse into carbon and oxygen. This is the helium flash, a moment of explosive ignition. Unlike the gentle hum of hydrogen fusion, the helium flash is a violent, runaway reaction. It's a stark contrast to the star's previous state, a sudden burst of energy in the core. The flash itself is fleeting, lasting just a few minutes, but it marks a turning point. The red giant's core is no longer inert. It's alive with fusion once more. The helium flash is a dramatic event, a star's last hurrah before it settles into its final phase. After the flash, the star enters a period of relative stability, fusing helium in its core and hydrogen in a shell around it. This is the horizontal branch phase, a brief interlude before the star's ultimate fate. The contrast between the red giant and the horizontal branch star is striking. The latter is smaller, hotter, and more stable, a far cry from the bloated, unstable red giant. But this stability is fleeting. Eventually, the star will exhaust its helium fuel, and the core will once again become inert. The outer layers will be ejected, forming a beautiful planetary nebula, while the core shrinks into a white dwarf. It's a cycle of birth, death, and rebirth, a testament to the universe's ceaseless creativity. Helium burning, the triple alpha process. In the grand theater of stellar evolution, the red giant phase marks a dramatic act, where our Sun and other Sun-like stars undergo a profound transformation. As the star's core, now a dense ball of inert helium, grows hotter and denser, it sets the stage for a spectacular chemical performance, the triple alpha process. This isn't a quick, explosive event, but a slow, deliberate dance of helium nuclei, each with 2 protons and 2 neutrons, seeking fusion. The core's temperature must reach a critical 100 million Kelvin, far hotter than the 15 million Kelvin needed for hydrogen burning. At this inferno-like temperature, helium nuclei begin to merge, forming unstable berylliumate. This fleeting isotope quickly decays, but in the dense core, some berylliumate nuclei collide with additional helium nuclei, creating a stable carbon-12 nucleus. 3 helium nuclei have fused, releasing energy and a tiny bit of mass as pure energy, according to Einstein's famous equation, E equals mc squared. This is the triple alpha process, the cosmic alchemy that forges carbon, the fourth most abundant element in the universe and the basis for life as we know it. The contrast between the red giant phase and the triple alpha process is stark. The red giant is a bloated, cool star, its outer layers expanding and cooling as the core contracts and heats up. It's a slow, steady process, like a simmering pot of soup. The triple alpha process, on the other hand, is a high-energy, high-temperature event, like a sudden burst of flame. Yet, both phases are crucial in the life of a sun-like star. The red giant phase provides the conditions for the triple alpha process, while the triple alpha process provides the energy to sustain the star against gravitational collapse. It's a delicate balance, a cosmic dance of creation and destruction. As the triple alpha process continues, the star's core becomes a bustling foundry, forging not just carbon, but also oxygen, neon, and magnesium. Each element is a testament to the star's life, a marker of its journey from a simple cloud of hydrogen and helium to a complex, multi-layered star. The outer layers of the star, meanwhile, continue to expand and cool, glowing with a reddish hue. This is the red giant, a star in its twilight years, yet still vibrant and active. It's a stark contrast to the hot, dense core, where the triple alpha process rages on. The star's fate is sealed, but it's not going down without a fight. It's creating, transforming, evolving, right up until the end. The horizontal branch, stability in the red giant phase. Stars, much like living beings, go through a life cycle, and for sun-like stars, the journey from the main sequence to the red giant phase is a dramatic transformation. After exhausting the hydrogen in their cores, these stars begin to swell, their outer layers cooling and expanding, turning them into red giants. This phase is a tumultuous one, marked by instability and change. Yet, amidst this chaos, there exists a period of relative calm, the horizontal branch. Picture a star, now a red giant, having shed its outer layers, standing tall and stable. It has found a new equilibrium, burning helium in its core instead of hydrogen. This is the horizontal branch, a phase where the star's temperature stabilizes and it settles into a steady rhythm. The star, once a tumultuous red giant, now hums a steady tune, a testament to its newfound stability. It's a stark contrast to the previous phase, where the star was a seething, unstable mass. The horizontal branch is a respite, a moment of calm before the storm that will eventually lead to the star's demise. During this phase, the star's core is a bustling hub of activity. Helium nuclei fuse to form carbon, releasing energy that counteracts the star's gravitational pull. This delicate balance keeps the star stable, allowing it to shine brightly and steadily. The star's outer layers, now less turbulent, expand and cool, emitting a reddish hue. It's a stark contrast to the blue-white glow of the main sequence phase. The star, now on the horizontal branch, is a beacon of stability, a testament to the star's ability to adapt and endure. Yet, this stability is not eternal. The star's core is slowly depleting its helium fuel, and the outer layers continue to expand. The star, once a steady beacon, begins to wobble. It's a prelude to the next phase, the asymptotic giant branch, where the star will once again become unstable, shedding its outer layers and forming a planetary nebula. The horizontal branch, therefore, is a brief interlude, a moment of stability in the otherwise tumultuous life of a sun-like star. It's a stark reminder of the constant change and adaptation that characterizes the life cycle of stars. The asymptotic giant branch, final stages of red giant evolution. Stars, like living organisms, go through a life cycle, and for sun-like stars, the end is a spectacular display of cosmic artistry. After the red giant phase, these stars enter the asymptotic giant branch, AGB, a final act of stellar evolution that is as dramatic as it is beautiful. Picture a star, now swollen and luminous, pulsating like a heartbeat, shedding its outer layers in a slow, graceful dance. This is the AGB phase, a time of intense activity and transformation. The star's core, now a dense, hot ball of helium and carbon, struggles to maintain equilibrium as it fuses heavier elements. Meanwhile, the outer layers, mostly hydrogen and helium, expand and cool, creating a vast, glowing envelope that can stretch out to hundreds of times the star's original size. Contrast this with the earlier red giant phase, where the star was more stable, burning helium in its core while a hydrogen-burning shell provided additional energy. The AGB phase is more chaotic, with the star undergoing thermal pulses, periods of increased fusion activity that cause the star to brighten and expand even further. These pulses can last for thousands of years, with the star's luminosity increasing by factors of hundreds or even thousands. It's as if the star is gasping for breath, taking in vast amounts of energy in a desperate attempt to prolong its life. The outer layers, now tenuous and extended, are subject to strong stellar winds that carry away vast amounts of material. This material, enriched with heavy elements forged in the star's core, seeds the interstellar medium, providing the raw materials for new stars and planets. The AGB phase is also marked by a stark contrast in temperature. While the core is incredibly hot, reaching temperatures of millions of degrees, the outer layers are relatively cool, with surface temperatures often below 30 Kelvin. This temperature difference creates a stark divide within the star, with the inner regions undergoing violent nuclear reactions while the outer layers remain relatively placid. The star's appearance changes dramatically as well, with the cool outer layers emitting most of their light in the infrared part of the spectrum. To an observer, the star would appear red and bloated, a far cry from the yellow dwarf it once was. As the AGB phase progresses, the star's fate becomes increasingly clear. The thermal pulses become more frequent and more violent, with each one stripping away more of the star's outer layers. Eventually, the star can no longer hold on to its outer envelope, and it begins to shed its material in a dramatic fashion. This material forms a vast, glowing nebula around the star, a prelude to the planetary nebula that will form in the final stages of the star's life. The star itself, now a tiny, hot core, will eventually collapse to form a white dwarf, a dense, Earth-sized remnant that will slowly cool and fade over billions of years. But for now, the AGB phase is a time of drama and transformation, a final hurrah before the star's inevitable demise. Mass loss, shedding stellar layers. Stars, much like living organisms, go through a life cycle, and for sun-like stars, the journey culminates in a spectacular display of color and light. As these stars age, they enter the red giant phase, swelling to sizes hundreds of times their original diameter. This expansion is a prelude to a dramatic process, mass loss. The star, now a bloated and cooling red giant, begins to shed its outer layers, creating a stellar wind that carries away vast amounts of material. This wind is not a gentle breeze but a fierce, hot gale, carrying with it the star's atmosphere, enriched with heavy elements forged in its core. The star, once a stable, shining orb, now pulsates and quivers, its surface roiling like a stormy sea, as it expels its outer layers into the cosmos. The contrast between the red giant phase and the subsequent planetary nebula phase is stark. The red giant, a bloated and cool star, is a stark contrast to the hot, dense core it will eventually become. As the star sheds its layers, the core, now exposed, begins to heat up. The expelled gas, once part of the star's atmosphere, is bathed in intense ultraviolet radiation from the hot core, causing it to glow with a myriad of colors. The once swollen red giant is now a tiny, dense white dwarf, surrounded by a beautiful, glowing shell of gas. This shell, the planetary nebula, is a fleeting spectacle, lasting only a few tens of thousands of years before dispersing into the interstellar medium. The process of mass loss is not uniform. Some stars shed their layers in a relatively quiet manner, while others undergo violent eruptions, expelling vast amounts of material in a short period. The exact mechanism of mass loss is complex and not fully understood, but it is thought to be driven by a combination of factors, including pulsations, radiation pressure, and magnetic fields. The expelled material forms a complex, often asymmetric, structure around the star, shaped by the interplay of these forces. This structure can take on a variety of forms, from simple spherical shells to intricate, filamentary networks, each a testament to the star's final, dramatic act. The mass loss process is not just a spectacular display, but also a crucial one. The expelled material enriches the interstellar medium with heavy elements, providing the raw materials for new stars and planets. In fact, every atom of carbon in our bodies, every oxygen atom in the air we breathe, was once part of a star, expelled into the cosmos in a stellar wind. Thus, the death of a sun-like star is not an end, but a beginning, a cycle of stellar life and death that has been playing out in our galaxy for billions of years. The red giant and its subsequent planetary nebula are not just beautiful objects, but also a reminder of our cosmic origins, a connection to the stars that we can see in the night sky. Planetary nebulae, the beautiful final act. In the grand theater of the cosmos, stars like our sun put on a spectacular show as they approach the end of their lives. After billions of years of burning hydrogen into helium, these stars enter a phase known as the red giant stage. Here, they swell to enormous sizes, engulfing any nearby planets in their fiery embrace. The once stable star, now a bloated and unstable red giant, pulsates and sheds its outer layers, creating a stunning display of stellar drama. This is the prelude to the final act, the Planetary Nebula, a breathtaking finale that outshines even the most vibrant supernovae. As the red giant sheds its outer layers, it reveals the hot, dense core that will become a white dwarf. This core, now exposed, emits intense ultraviolet radiation that ionizes the expelled gas, causing it to glow in a dazzling array of colors. The once symmetrical red giant has transformed into a complex, asymmetrical nebula, with intricate patterns and structures that resemble everything from delicate bubbles to intricate sculptures. Each planetary nebula is unique, a testament to the individuality of the star that created it. The gas and dust expelled in this phase enriched the interstellar medium, seeding the universe with the building blocks for new stars and planets. The contrast between the red giant phase and the planetary nebula phase is stark. The red giant is a slow, steady process, a star in its twilight years, gently shedding its outer layers. The planetary nebula, on the other hand, is a rapid, dynamic event, a star's final hurrah before it fades into obscurity as a white dwarf. The colors, too, are a study in contrasts. The red giant, true to its name, glows with a reddish hue, a sign of its cool, swollen state. The planetary nebula, however, is a riot of colors, from the blues and greens of oxygen to the reds and pinks of hydrogen, a stark reminder of the star's violent end. In many ways, the planetary nebula is the star's swan song, a final, beautiful act before it fades away. It's a fitting end for a star that has spent billions of years shining brightly. And while the star may be gone, its legacy lives on in the planetary nebula, a testament to the star's life and the universe's constant cycle of death and rebirth. So, when you look up at the night sky, remember that what you're seeing is not just a star, but a story, a tale of life, death, and the beauty that can be found in both. The formation of planetary nebulae. In the vast theater of the cosmos, stars like our sun put on a spectacular show as they approach the end of their lives. After billions of years of converting hydrogen into helium through nuclear fusion, these stars begin to swell, their outer layers expanding and cooling to form a red giant. This phase is a dramatic transformation, a stark contrast to the stable, middle-aged star that came before. The red giant phase is a time of turmoil, with the star's outer layers pulsating and shedding material into the surrounding space. This ejected material, a mix of gas and dust, is enriched with heavy elements forged in the star's core, seeding the universe with the building blocks of new stars and planets. As the red giant continues to lose mass, its core shrinks and heats up. The star's outer layers, now more distant from the hot core, become increasingly tenuous and diffuse. This sets the stage for the formation of a planetary nebula, a celestial spectacle that is as beautiful as it is fleeting. The hot core, now exposed, emits intense ultraviolet radiation that ionizes the surrounding gas, causing it to glow in a dazzling array of colors. The once red giant has now become a planetary nebula, a shimmering jewel in the cosmic crown. This phase is a stark contrast to the red giant stage, a transition from a bloated, cooling star to a compact, hot core surrounded by a glowing shell of gas. The formation of a planetary nebula is a complex process, a dance of gravity, radiation, and stellar winds. The shape of the nebula can vary widely, from simple spheres to intricate, asymmetric structures. This diversity is thought to be influenced by the presence of companion stars or planets, which can shape the ejected material through their gravitational pull. The nebula's appearance can change over time, as the ionized gas expands and disperses into the interstellar medium. This process can take tens of thousands of years, a blink of an eye in the lifespan of a star. Eventually, the nebula will fade, leaving behind the exposed core of the star, now a white dwarf, to slowly cool and dim over billions of years. The role of stellar winds in planetary nebulae formation. In the grand theater of the cosmos, stars like our Sun put on a spectacular show as they approach the end of their lives. After billions of years of burning hydrogen in their cores, these stars swell into red giants, their outer layers puffing up like a balloon, engulfing any nearby planets. This phase is a dramatic transformation, a stark contrast to the stable, middle-aged star they once were. The red giant phase is marked by intense stellar winds, which play a pivotal role in the next act of this stellar drama, the formation of planetary nebulae. These stellar winds are not gentle breezes, but rather powerful streams of charged particles and gas, hurtling into space at speeds of several kilometers per second. They carry away a significant portion of the star's mass, creating a vast envelope of material around the star. As the red giant exhausts its nuclear fuel, it begins to shed its outer layers more vigorously. The core, now exposed, is a hot, dense ember, emitting intense ultraviolet radiation. This radiation ionizes the surrounding gas, causing it to glow in a dazzling array of colors, forming what we see as a planetary nebula. The contrast between the red giant phase and the planetary nebula phase is striking. The red giant is a bloated, cool star, its surface a tapestry of convective currents. In contrast, the planetary nebula is a complex, dynamic structure with intricate shapes and patterns. The stellar winds, now carrying the star's outer layers, interact with the interstellar medium, creating shock waves and instabilities. These winds sculpt the nebula, shaping it into rings, bipolar structures, or even more complex forms. The hot core, now a white dwarf, continues to illuminate the nebula, its ultraviolet radiation driving the ionization and excitation of the gas. The role of stellar winds in planetary nebula formation is crucial. They not only carry away the star's outer layers, but also shape the nebula's structure and evolution. The winds can create density variations in the nebula, leading to the formation of filaments and knots. They can also trigger instabilities, causing the nebula to fragment and evolve in complex ways. The interaction between the stellar winds and the interstellar medium can create bow shocks, which further shape the nebula. In essence, the stellar winds are the choreographers of this cosmic ballet, guiding the transformation of a red giant into a planetary nebula. The central star, the remnant of the red giant. In the grand theater of the cosmos, stars like our Sun often meet their end in a spectacular display of light and color, transforming into red giants before leaving behind a glowing planetary nebula. At the heart of this dramatic finale lies the central star, a remnant that has shed its outer layers, revealing a dense, hot core. This core, once the powerhouse of nuclear fusion, now stands exposed, radiating intensely in ultraviolet light. It's a stark contrast to the star's former self, a testament to the violent, yet beautiful process of stellar evolution. Picture a star, once a stable, middle-aged yellow dwarf, now bloated and red, shedding its outer layers like an aging actor discarding old costumes. This is the red giant phase, a tumultuous time marked by instability and change. The central star, the core of this red giant, is a dense, hot ball of helium and other elements, a mere fraction of the star's original size. It's a stark contrast to the bloated red giant, a tiny, intense beacon compared to the star's former, more sedate appearance. As the red giant sheds its outer layers, it forms a planetary nebula, a glowing, colorful cloud of gas and dust. At the center of this nebula, the central star continues to radiate intensely, ionizing the surrounding gas and causing it to glow. The central star is now a white dwarf, a dense, Earth-sized remnant that will slowly cool and fade over billions of years. It's a stark contrast to the vibrant, glowing nebula, a quiet, cooling ember compared to the fiery display of the nebula's creation. The central star's journey doesn't end with the formation of the planetary nebula. It continues to evolve, cooling and dimming over time. It's a slow, steady process, a stark contrast to the rapid, violent changes of the red giant phase. The central star, once the heart of a vibrant, active star, now sits quietly at the center of a glowing nebula, a testament to the ever-changing nature of the universe. It's a stark reminder that even in death, stars continue to shape and influence their surroundings, leaving behind a legacy that will last for billions of years. The shape and structure of planetary nebulae. Planetary nebulae are the mesmerizing, colorful clouds of gas and dust that form around dying stars, much like our Sun. They are born from the outer layers of a red giant star, which are ejected into space as the star transitions into a white dwarf. The shape and structure of these nebulae are as varied as they are stunning, with some appearing as simple spheres, while others take on the forms of bipolar lobes, rings, or even intricate, asymmetrical shapes. This diversity is a testament to the complex processes at play during a star's final stages. The transformation from a red giant to a planetary nebula is a dramatic one. Picture a once giant star, swollen and red, shedding its outer layers like a snake shedding its skin. These layers, now free from the star's gravitational pull, are illuminated by the intense ultraviolet radiation from the exposed hot core. The result is a glowing, ethereal shell of gas and dust, with the tiny white dwarf star nestled in the center, like a jewel in a crown. The contrast between the red giant's slow, steady burning and the planetary nebula's vibrant, dynamic display is stark. The shapes of planetary nebulae are influenced by a variety of factors, including the star's rotation, the presence of a companion star, and the magnetic fields within the star's atmosphere. Some nebulae exhibit symmetrical, bipolar structures, with twin lobes of gas and dust extending in opposite directions. Others appear more chaotic, with irregular shapes and complex patterns. The Helix Nebula, for instance, resembles a giant eye, with a glowing, donut-shaped ring of gas and dust surrounding a white dwarf star. In contrast, the Butterfly Nebula displays a striking, symmetrical hourglass shape, with twin lobes of gas and dust extending from a narrow waist. The structure of planetary nebulae is equally fascinating. The outer shell of gas and dust is often composed of hydrogen, helium, and other elements, with the heavier elements concentrated in the inner regions. This is a result of the star's nuclear fusion processes, which create heavier elements in the star's core. As the star sheds its outer layers, these elements are dispersed into space, enriching the interstellar medium and providing the raw materials for new stars and planets. The white dwarf star at the center of the nebula continues to shine, its intense radiation ionizing the surrounding gas and causing it to glow in a dazzling array of colors. This dance of light and shadow, of creation and destruction, is a fitting finale for a star like our Sun. The role of binary systems in planetary nebulae formation. In the vast theater of the cosmos, stars like our Sun perform a dramatic finale as they approach the end of their lives. These celestial bodies, after billions of years of steady brilliance, swell into colossal red giants, their outer layers puffing up like a balloon ready to burst. This phase is a stark contrast to their earlier, more stable years. The star's core, a dense and fiery heart, continues to churn, fusing hydrogen into helium. Meanwhile, the outer layers, now cool and bloated, expand far beyond the star's original boundaries. It's a slow, inevitable transformation, a star's last gasp before it sheds its outer layers in a spectacular display. Enter the binary systems, where two stars orbit a common center. These cosmic dance partners play a crucial role in the formation of planetary nebulae, the glowing remnants of dying stars. In a binary system, the red giant's bloated atmosphere can be stripped away by its companion star. This gravitational tug-of-war causes the red giant to lose its outer layers prematurely, creating a stunning nebula. The contrast here is striking. The once solitary star now shares its fate with another, their destinies intertwined in a celestial waltz. The companion star, often smaller and less massive, acts as a cosmic sculptor, shaping the nebula's intricate patterns. Without this partner, the red giant might have faded away quietly, its death unnoticed. The process is anything but gentle. The red giant's outer layers are torn away, revealing the hot, dense core beneath. This core, now exposed, emits intense ultraviolet radiation that ionizes the surrounding gas, causing it to glow. The result is a planetary nebula, a shimmering cloud of gas and dust that can span light years. The companion star, meanwhile, continues its orbit, a silent witness to the transformation. The contrast between the two stars is stark. One, a dying giant, sheds its layers in a final burst of glory. The other, a smaller, cooler star, watches from the sidelines. It's a cosmic ballet, a dance of death and rebirth. In some cases, the companion star can even trigger a nova, a sudden, intense burst of light. This happens when the red giant's outer layers fall onto the companion star, igniting a thermonuclear explosion. The contrast here is dramatic. A quiet, unassuming star suddenly becomes a beacon of light, outshining entire galaxies. The nova, however, is fleeting. It fades away, leaving behind a planetary nebula and a companion star that continues its orbit, a silent testament to the drama that unfolded. The red giant, now stripped of its outer layers, becomes a white dwarf, a dense, Earth-sized remnant that slowly cools over billions of years. It's a stark reminder of the cycle of life and death in the cosmos. The chemical composition of planetary nebulae. Planetary nebulae are the glowing, colorful remnants of sun-like stars in their final stages of life. They are not, despite the name, related to planets. Instead, they are vast clouds of gas and dust, expelled by the star as it transitions into a white dwarf. The chemical composition of these nebulae is a rich tapestry, woven with elements forged in the star's core over billions of years. Helium and carbon are prominent, but so too are nitrogen, oxygen, and even heavier elements like neon and magnesium. These elements are not uniformly distributed. Instead, they clump and swirl in intricate patterns, creating the stunning images captured by telescopes like Hubble. The journey from red giant to planetary nebula is a dramatic transformation. Picture a star, swollen and red, shedding its outer layers like an aging giant discarding old clothes. This is the red giant phase, a slow, steady process that can last for hundreds of millions of years. The star's core, meanwhile, is a bustling factory, fusing elements and creating the very stuff that will one day form new stars and planets. When the star can no longer sustain fusion, it ejects these enriched layers into space. This material, now a planetary nebula, is a cosmic recycling plant, spreading newly minted elements across the galaxy. The contrast between the red giant and planetary nebula phases is stark. The red giant is a bloated, cool star, its surface a roiling sea of convection currents. It pulses and throbs, shedding material in fits and starts. The planetary nebula, by contrast, is a dynamic, evolving entity. It is shaped by the interplay of radiation from the central star, stellar winds, and the magnetic fields of the ejected material. The result is a dazzling array of shapes and structures, from simple spheres to complex bipolar nebulae with intricate symmetries. Each nebula is unique, a testament to the star's history and the conditions of its environment. The chemical composition of planetary nebulae is not just a pretty sight. It's a crucial part of the universe's life cycle. These nebulae enrich the interstellar medium with heavy elements, providing the raw materials for new stars and planets. In fact, every atom of carbon in your body was once part of a planetary nebula. The next time you see an image of a planetary nebula, remember that you are looking at the death of a star and the birth of the next generation of celestial bodies. It's a humbling thought, a reminder of our place in the grand scheme of the cosmos. The role of planetary nebulae in galactic chemical evolution. In the grand theater of the cosmos, stars like our Sun put on a spectacular show as they approach the end of their lives. They swell into red giants, bloated and fiery, shedding their outer layers in a dramatic display. These layers, now free from the star's gravitational grasp, form a glowing, colorful shell known as a planetary nebula. It's a stark contrast to the star's previous life, a brief but brilliant finale before the core collapses into a white dwarf. The term planetary nebula is a misnomer, a relic of early astronomers who thought these objects resembled planets. In reality, they are the graveyards of low and medium-mass stars, the remnants of a star's final breath. Planetary nebulae are more than just beautiful cosmic spectacles. They play a crucial role in the chemical evolution of galaxies. As the outer layers of the red giant are expelled, they carry with them a rich tapestry of elements. These elements, forged in the star's core through nuclear fusion, are now scattered into the interstellar medium. Here, they can become the building blocks for new stars and planets. The process is akin to a cosmic recycling program, where the death of one star enriches the galaxy, enabling the birth of new ones. The elements expelled include carbon, nitrogen, and oxygen, which are essential for life as we know it. In this way, planetary nebulae are the galaxy's way of spreading wealth, ensuring that future generations of stars have the necessary ingredients to create worlds and, potentially, life. The transformation from red giant to planetary nebula is a stark contrast, a dramatic shift in both appearance and role. The red giant, a bloated and aging star, is a slow, steady burner. It's a phase where the star is shedding its outer layers, a process that can take thousands of years. The planetary nebula, on the other hand, is a brief, brilliant phase. It's a shell of ionized gas, glowing with the light of the exposed core, now a white dwarf. This phase lasts only about 10 years, a mere blink of an eye in the lifespan of a star. Yet, in this short time, the planetary nebula plays a vital role in enriching the galaxy with heavy elements. It's a poignant reminder of the cycle of life and death in the universe, a cycle that has been repeating for billions of years and will continue long after our Sun has met its own end. The life cycle of planetary nebulae. In the vast theater of the cosmos, stars like our Sun perform a dramatic finale, a spectacle of light and color that transforms them from red giants into ethereal planetary nebulae. This life cycle is a mesmerizing dance of stellar evolution, a process that begins with the star's final stages of life. As a red giant, the star has already exhausted the hydrogen in its core, causing it to expand and cool. It's a bloated, aging star, shedding its outer layers in a gentle solar wind. Picture a once vibrant performer, now a seasoned artist, sharing the wisdom of its years with the universe. The curtain rises on the next act when the star's core, now composed primarily of helium, begins to contract and heat up. This is the denouement, the star's last hurrah. The intense heat ignites the helium, causing the star to briefly swell and brighten. But this is not a permanent state. The star is running out of time, its fuel nearly spent. The outer layers, now a mix of hydrogen and helium, are expelled into space at speeds of up to 30 kilometers per second. This ejected material forms a glowing, expanding shell of gas and plasma, the planetary nebula. It's a stunning display, a cosmic butterfly emerging from its stellar chrysalis. The contrast between the red giant and planetary nebula phases is stark. The red giant is a slow, steady process, a star gently shedding its layers like an aging actor removing their makeup. The planetary nebula, on the other hand, is a rapid, dynamic event. The star's core, now exposed, is a small, hot white dwarf. It's a stark contrast to the bloated red giant, a tiny, intense light compared to the diffuse, glowing nebula. The white dwarf will slowly cool and fade over billions of years, but the planetary nebula is a fleeting spectacle. It lasts only about 10 years, a brief, brilliant interlude in the star's life cycle. The life cycle of planetary nebulae is a testament to the universe's constant cycle of death and rebirth. The expelled material from the red giant enriches the interstellar medium with heavy elements, providing the raw materials for new stars and planets. It's a cosmic recycling program, a never-ending cycle of stellar evolution. Each planetary nebula is unique, a testament to the individuality of each star. Some are spherical, others bipolar, some even display complex, symmetrical patterns. They are the universe's way of reminding us that even in death, there is beauty and creation. The fate of the central star, white dwarfs. In the grand theater of the cosmos, stars like our Sun meet their end in a dramatic, yet graceful, performance. After swelling into a red giant and shedding their outer layers to create a planetary nebula, the core of the star is left exposed. This core, once the powerhouse of nuclear fusion, now settles into a new role as a white dwarf. White dwarfs are the dense, Earth-sized remnants of Sun-like stars, packing a mass comparable to that of the Sun into a volume no larger than our planet. They are the ghosts of stars past, glowing faintly with the residual heat of their former lives. The transformation from a red giant to a white dwarf is a stark contrast. Picture a once mighty star, now a bloated red giant, casting off its outer layers in a spectacular display of light and color. These layers, now ionized by the intense ultraviolet radiation from the exposed core, form the beautiful and intricate structures of planetary nebulae. Meanwhile, the core itself undergoes a dramatic collapse. Electrons and nuclei are forced into a tight embrace, creating a degenerate matter that resists further compression. The result is a white dwarf, an object with a density so high that a teaspoon of its material would weigh several tons on Earth. White dwarfs are not merely passive remnants. They are dynamic and intriguing objects. They start their lives as extremely hot, with surface temperatures ranging from 100 to 200 Kelvin. Over billions of years, they slowly cool down, fading from white to red and eventually becoming black dwarfs, though none are thought to exist in the universe yet. Some white dwarfs have companions, and in these cases, they can exhibit fascinating behaviors. If a white dwarf is part of a binary system, it can pull material from its companion, leading to nova outbursts or even type I supernovae, which are crucial for studying the expansion of the universe. The fate of a white dwarf is also influenced by its mass. If it exceeds the Chandrasekhar limit, about 1.4 times the mass of the Sun, it can no longer support itself against gravity and will collapse, potentially leading to a supernova. However, most white dwarfs remain stable, slowly cooling and fading into the cosmic night. They are the final act in the life cycle of Sun-like stars, a poignant reminder of the transient nature of celestial bodies. In their quiet, fading glow, white dwarfs whisper the stories of their past, a testament to the ever-changing cosmos. The white dwarf cooling sequence. In the grand theater of the cosmos, stars like our Sun put on a spectacular show as they approach the end of their lives. After billions of years of shining brightly, they swell into red giants, their outer layers puffing up like a balloon filled with glowing gas. This phase is a stark contrast to their earlier, more stable years. The star's core, now a dense nugget of helium, burns hot and bright, while the outer layers cool and expand, turning a deep, fiery red. It's a dramatic transformation, a star's last hurrah before it settles down into a quieter, more sedate existence. As the red giant phase winds down, the star begins to shed its outer layers, creating a beautiful, glowing planetary nebula. This nebula, a vast cloud of gas and dust, is illuminated by the intense ultraviolet radiation from the star's exposed core. The nebula's colors shift and change, a kaleidoscope of hues that reflect the different elements present. Oxygen glows green, hydrogen shines red, and nitrogen emits a deep blue light. It's a stunning display, a final farewell from a star that has burned brightly for billions of years. At the heart of this nebula lies the star's core, now a white dwarf. This tiny, dense object is all that remains of the original star. It's a stark contrast to the glowing nebula that surrounds it, a silent sentinel that will slowly cool and fade over billions of years. This is the white dwarf cooling sequence, a gradual process that sees the star's temperature drop, its light dim, and its color shift from white to red to black. It's a slow, inexorable process, a star's final journey from the fiery brilliance of its youth to the cold, dark silence of old age. The white dwarf cooling sequence is a fascinating process, a testament to the incredible diversity and complexity of the universe. It's a stark reminder of the fleeting nature of life, even for stars that burn for billions of years. Yet, it's also a beautiful process, a final display of the star's incredible power and beauty. As the white dwarf cools and fades, it leaves behind a legacy, a planetary nebula that will continue to shine for thousands of years, a final tribute to the star that once was. The role of white dwarfs in type I supernovae. In the grand theater of the cosmos, stars like our Sun meet their end in a spectacular display of light and color, culminating in the formation of ethereal planetary nebulae and the birth of white dwarfs. These stellar remnants, though small, pack a significant punch. White dwarfs are the dense cores left behind after a star has shed its outer layers. They are Earth-sized but contain a mass comparable to that of the Sun. Their gravity is so intense that they crush matter into an exotic state of matter, neither solid, liquid, nor gas. Yet, their story doesn't end with their formation. Instead, they often play a pivotal role in one of the most powerful events in the universe, type I supernovae. Picture a white dwarf, a once mighty star now reduced to a dim, dense husk, orbiting another star in a binary system. If the conditions are right, the white dwarf can begin to steal material from its companion. This stolen fuel can reignite nuclear fusion on the white dwarf's surface, leading to a nova. But there's a tipping point. If the white dwarf's mass grows to about 1.4 times that of the Sun, a threshold known as the Chandrasekhar limit, it becomes unstable. The core temperature soars, igniting runaway nuclear fusion. In a matter of seconds, the white dwarf explodes in a type I supernova, outshining entire galaxies and releasing an enormous amount of energy. The contrast between the serene beauty of a planetary nebula and the cataclysmic violence of a type I supernova is stark. The planetary nebula phase is a gentle farewell, a star's outer layers drifting away to form a glowing shell of gas and dust. It's a slow, graceful process, like a dancer's final bow. The supernova, on the other hand, is a sudden, explosive encore. The white dwarf, once a quiet observer, becomes the star of the show, tearing itself apart in a blaze of glory. Yet, both phases are integral to the life cycle of stars, each playing a crucial role in the universe's grand recycling of matter. In the aftermath of a type I supernova, nothing remains of the white dwarf. It has given everything in its final performance, leaving behind only a faint, rapidly expanding remnant. Yet, its legacy lives on. Type I supernovae are crucial tools for astronomers, acting as standard candles to measure cosmic distances. They have been instrumental in the discovery of dark energy, the mysterious force driving the acceleration of the universe's expansion. So, while the white dwarf may be gone, its impact on our understanding of the cosmos is immeasurable. It's a humble reminder that even in death, stars continue to shape the universe. Observing planetary nebulae, tools, and techniques. Planetary nebulae, the glowing remnants of dying sun-like stars, are a sight to behold. They are born from the final stages of a star's life, a dramatic transformation from a red giant to a white dwarf. Observing these celestial objects requires a blend of tools and techniques, each revealing different aspects of their beauty and complexity. Telescopes, both ground-based and spaceborne, are the primary tools for this endeavor. Ground-based telescopes, like the Hubble Space Telescope, offer high-resolution images, capturing the intricate details of the nebula structure. Space telescopes, on the other hand, provide a clearer view by avoiding atmospheric interference, allowing astronomers to study the nebula's spectrum and chemical composition. The contrast between the red giant phase and the planetary nebula phase is stark. A red giant is a bloated, cool star, shedding its outer layers in a slow, gentle process. It's like watching a slow-motion explosion, a star gently letting go of its outer layers. In contrast, a planetary nebula is a hot, dense core surrounded by a glowing shell of ionized gas. It's a dramatic finale, a star's last hurrah before fading into a white dwarf. This transformation is not just visual, but also chemical. The red giant's gentle winds carry elements like carbon and nitrogen into space, enriching the interstellar medium. The planetary nebula, with its intense ultraviolet radiation, ionizes these elements, creating the vibrant colors seen in images. To observe these changes, astronomers use a variety of techniques. Spectroscopy, for instance, splits light into its component colors, revealing the nebula's chemical composition and physical conditions. Imaging, on the other hand, captures the nebula's structure and morphology. Each technique offers a different perspective, a unique window into the life and death of a star. For example, the Helix Nebula, one of the closest planetary nebulae to Earth, appears as a glowing eye in images, its intricate details revealed by high-resolution imaging. Its spectrum, analyzed through spectroscopy, shows the presence of various elements, each telling a story of the star's life and death. Moreover, advanced techniques like interferometry combine the light from multiple telescopes, offering even higher resolution. This allows astronomers to study the nebula's kinematics, the motion of its gas and dust. For instance, the water maser emissions in the Planetary Nebula K3-30-5 were studied using interferometry, revealing the complex dynamics of its outflow. Each tool and technique, from imaging to spectroscopy to interferometry, paints a different picture of these celestial objects. Together, they provide a comprehensive understanding of the death of sun-like stars, a testament to the power of human curiosity and ingenuity. Notable examples of planetary nebulae. Planetary nebulae are the mesmerizing, colorful clouds of gas and dust that form around dying stars, much like our sun. They are born from the final stages of a star's life, a dramatic transformation that begins with the red giant phase. As the star exhausts its nuclear fuel, it sheds its outer layers, creating a glowing, ethereal shell of ionized gas. This process reveals the star's hot, dense core, which will eventually cool and fade as a white dwarf. The contrast between the red giant's slow, bloated demise and the planetary nebula's vibrant, energetic display is stark, a cosmic ballet of light and color. Among the most notable examples of planetary nebulae is the Helix Nebula, often referred to as the Eye of God. This intricate structure, located about 700 light-years away in the constellation Aquarius, presents a stunning, donut-shaped appearance. Its central star, a white dwarf, illuminates the surrounding gas, creating a vivid display of greens, blues, and reds. The Helix Nebula's complex patterns and filaments are a testament to the turbulent processes that accompany a star's death. Another remarkable example is the Ring Nebula, situated in the constellation Lyra. This nebula, with its distinctive elliptical shape and glowing, expanding ring, offers a clear view of the star's final stages. The central white dwarf, a tiny, Earth-sized remnant, sits at the heart of the nebula, casting a haunting glow on the surrounding gas. The Cat's Eye Nebula, found in the constellation Draco, is another striking example. Its intricate, nested structures and high-velocity outflows create a captivating visual spectacle. The nebula's central star, a binary system, adds an extra layer of complexity to its formation. Each of these planetary nebulae tells a unique story, a final, dramatic chapter in the life of a sun-like star. They serve as cosmic laboratories, providing astronomers with valuable insights into the processes of stellar evolution and the eventual fate of our own Sunday. The contrast between the red giant's slow, bloated demise and the planetary nebula's vibrant, energetic display is stark, a cosmic ballet of light and color. The future of our sun, a red giant and planetary nebula destiny. In the far-off future, our sun, much like many other stars of its kind, will undergo a dramatic transformation. It will first swell into a red giant, a phase that will last for billions of years. During this time, the sun will expand, engulfing Mercury and Venus, and possibly even Earth. Its surface will cool, taking on a reddish hue, and it will shine with a dimmer light. The once vibrant star will seem sluggish, like an old giant resting after a long journey. It will pulse and pulsate, shedding its outer layers in a slow, steady process. This is the inevitable fate of stars like our sun, a destiny written in the stars from the moment they were born. As the red giant phase comes to an end, the sun will begin to shed its outer layers more rapidly. These layers, composed of gas and dust, will drift away from the star, forming a beautiful, glowing shell of ionized gas. This is the birth of a planetary nebula, a fleeting yet spectacular phase in the life of a star. The name is a misnomer, coined by early astronomers who thought these objects resembled planets. In reality, they are the final breaths of dying stars, a last hurrah before the star's core collapses into a white dwarf. The planetary nebula will glow with an ethereal light, a stark contrast to the red giant's dull shine. It will be a brief, brilliant finale, a cosmic dance of light and color. The white dwarf that remains after the planetary nebula fades is a dense, Earth-sized core, the remnants of the sun's once mighty interior. It will be a ghost of the star it once was, a silent sentinel in the night sky. The white dwarf will slowly cool over trillions of years, eventually fading into a cold, dark husk. This is the ultimate fate of our sun, a journey from a fiery youth to a quiet, unassuming end. It's a stark reminder of the impermanence of all things, even the stars that light our way. Yet, in this end, there is beauty. The red giant and planetary nebula phases are a testament to the sun's life, a final, spectacular display before it rests. The significance of studying red giants and planetary nebulae. Red giants and planetary nebulae mark the dramatic final acts in the life of a sun-like star. These phases, though fleeting in cosmic terms, are pivotal in the grand cycle of stellar life and death. Red giants are swollen, cooling stars that have exhausted the hydrogen in their cores. They glow with a reddish hue, their surfaces bloated to hundreds of times their original size. Picture a once vibrant star, now a gentle, aging giant, shedding layers of gas into the cold expanse of space. This phase is a stark contrast to the star's earlier life, when it burned brightly and steadily. The red giant phase is a slow, deliberate process, a star's last attempt to fuse heavier elements in its core. It's a time of transformation, a prelude to the more spectacular planetary nebula phase. Planetary nebulae are the stunning, colorful clouds of gas and dust expelled by red giants. They form when the outer layers of the red giant are ejected, revealing the hot, dense core, a white dwarf. These nebulae are often symmetrical, with intricate patterns that resemble everything from butterflies to hourglasses. The contrast between the red giant and planetary nebula phases is striking. The red giant is a slow, steady process, while the planetary nebula is a rapid, dynamic event. The nebula phase is relatively short, lasting only a few tens of thousands of years, a blink of an eye in the universe's timescale. Yet, it's during this phase that the star enriches the interstellar medium with heavy elements, seeding the next generation of stars and planets. Studying red giants and planetary nebulae offers profound insights into stellar evolution and the universe's chemical composition. These phases are crucial in understanding the life cycle of stars and the formation of planetary systems. Red giants, with their expanded atmospheres, provide a unique laboratory for studying nucleosynthesis, the process by which elements heavier than hydrogen and helium are created. Planetary nebulae, with their complex structures and emissions, offer a window into the final stages of stellar evolution. They also play a vital role in galactic ecology, distributing elements like carbon, nitrogen, and oxygen into the interstellar medium. These elements are the building blocks of planets and life as we know it. Moreover, the study of red giants and planetary nebulae has practical applications. They serve as cosmic distance indicators, helping astronomers measure the scale of the universe. They also provide clues about the age and composition of galaxies. By understanding these phases, scientists can better predict the future of our own sun, which will eventually go through similar stages. The death of sun-like stars is not an end, but a rebirth, a cycle that has been repeating since the universe began. Each red giant and planetary nebula is a testament to the universe's ceaseless creativity and the interconnectedness of all cosmic phenomena. As we've journeyed through the life cycle of sun-like stars, we've witnessed the dramatic transformation from a steady, reliable main-sequence star to a bloated, fiery red giant, and finally, to the ethereal beauty of a planetary nebula. The once humble star, now a cosmic artist, paints the universe with its final breath, creating a masterpiece that outshines its former self. It's a tale of grandeur and grace, a stellar performance that leaves us in awe. Imagine the contrast: the red giant, a swollen titan, shedding its outer layers like an ancient, weary king casting off his royal robes. The once familiar, steady light now flickers and pulses, casting long, dramatic shadows across the cosmic stage. Then, in a final act of defiance, the star casts off its outer layers, revealing the hot, dense core within. This core, now a white dwarf, illuminates the expelled gas, creating a planetary nebula that dances and shimmers in the vast expanse of space. This is not just a story of death, but of rebirth. The expelled gas and dust will one day form new stars and planets, continuing the cycle of life in the universe. It's a reminder that even in the face of inevitable change, there is beauty and hope. So, as we conclude our exploration of red giants and planetary nebulae, we invite you to join us on our next cosmic adventure. Subscribe to our channel and hit the bell icon to be notified when we dive into the mysteries of black holes, supernovae, and other stellar phenomena. Together, let's continue to explore the wonders of the universe, one star at a time. Until then, keep looking up, keep wondering, and keep exploring. The universe is waiting.